Hi there, this is Mr. Schnitzius. Today in this video, we are going to continue learning about coordinate proofs. And in particular, we're going to look at coordinate proofs for parallel and perpendicular lines. So in the last activity, we used coordinate proofs to prove that the midpoint formula is valid. And today we're going to prove properties and theorems about parallel and perpendicular lines. So Maria and Eric have been asked to prove the following theorem. Two non-vertical lines are parallel if and only if they have the same slope. So we learned about if and only if statements way back in the very beginning of this class in Unit 1. So just a reminder, an if and only if statement is called a biconditional statement. So that's a statement where the conditional statement is true and the converse is true. In other words, this theorem is true if both of these conditional statements are true. If two non-vertical lines are parallel, then they have the same slope. That's going to be Maria's job to prove that direction of the biconditional statement. Then later on, Eric is going to prove the converse of that statement. If two lines have the same slope, then they are parallel. So let's look at Maria's job in this proof. Here we have a picture where line L is parallel to line N. So let's go ahead and mark those two lines as parallel. Okay, so we've got a vertical line P that intersects line L at point A. We've also got a vertical line Q that intersects line N at point D right here. We've also got a horizontal line R that intersects line L at point C and line N at point F. So we've also got the intersection of line P and line R as point B. And we've got the intersection of line Q and line R as point E. So those are all the points that we're going to use to work out this proof. Okay, so we want to identify the segments that are parallel to the x-axis. That would be line segment BC, and line segment EF. Those are parallel to the x-axis. We also have some segments that are parallel to the y-axis. We've got segments AB and segment DE. And if you're looking carefully, now you see that we have two segments like this. And remember, we know that lines L and N are parallel. So if we have a vertical segment intersecting a horizontal segment at angle ABC, we know that that gives us a right angle. Same thing at angle DEF. Segment DE is vertical, segment EF is horizontal. So that gives us two right angles. And what do we know about two right angles? Any two angles that are both right angles have to be congruent to each other. So what does that tell us about angle ACB and angle DFE? Well, those angles are congruent because they are corresponding angles. Remember, if parallel lines are cut by a transversal, which in this case would be line R, then the corresponding angles formed are congruent. And so because we have two pairs of corresponding angles that are congruent to each other, the angle-angle similarity postulate tells us that triangle ABC and triangle DEF are similar to each other. Remember, that's what that tilde in between the two triangles tells us. Well, if we have two similar triangles. Let's go ahead and outline those similar triangles again. Here's one right triangle that's similar to the other right triangle. And remember, we knew that because our starting hypothesis was that lines L and N are parallel. When we have similar triangles, the corresponding sides are proportional. See segment AB over BC, that would be like the height the length of the height divided by the length of the base in triangle ABC is the same as the length of the height divided by the length of the base in triangle DEF. So by the definition of slope, the slope of line L is AB over BC. Remember, slope is rise over run. That's just a ratio. So the ratio of how much we're rising divided by how much we're running is the slope. And then for line for line N, that ratio, that rise over run ratio is DE, how much we're moving up, divided by EF, how much we're running over. So since this is showing that those two slopes are equal, that proves that if the lines are parallel, then the slopes are equal. So that's all we have to do in order to prove Maria's portion of the proof. We started out knowing that the lines are parallel, and we just proved that if lines are parallel, then the slopes are the same. The slopes are equal. So now we're going to look at the other direction of that proof. Now we're switching the hypothesis and the conclusion. This says, given that line L and line N have the same slope, our job is going to be to prove that lines L and N are parallel lines. So here's the picture we're going to use for this proof. Line L and N have the same slope. So we're going to draw a vertical line P that intersects line L at point A, and another vertical line Q that intersects line N at point D. This is actually the exact same picture with the exact same points that we had for Maria's part of the proof. Okie dokie. So based on the figure, it says that we can conclude that the ratio of AB divided by the length of BC is equal to the ratio of the length of segment DE divided by the length of segment EF. How do we know that we can do that? Well, we were told in the given information that these two lines have the same slope. So we saw in Maria's proof that this gives us the rise over run ratio for line L. This gives us the rise over run ratio for line N. So these are two slopes, and we were told that the slopes are equal. So we know that those ratios are the same. So as the next step in Eric's proof, he says that triangle ABC, this triangle on the left, is similar to triangle DEF by Sas Similarity Criteria. How is he allowed to do this? Well, we already have two pairs of corresponding sides that are proportional, and we know that angle B is congruent to angle E because they are right angles. So if we're looking for a side angle side similarity relationship, bottom side lengths are proportional. In between, we have two congruent angles. The lengths of the heights are proportional, so that's side angle side similarity. What is true about the angles of two similar triangles? Well, we know that corresponding angles are congruent. So now we've got angle BCA. Is that a corresponding angle with angle EFD? Yeah, those angles are corresponding, so that means that the corresponding angles have to be congruent. So let's go ahead and mark that those angles are congruent. All right, and remember, our goal was to prove that lines L and N are parallel. So can we say for sure that line L is parallel to line N? Well, yes, we can. If corresponding angles are congruent when two lines are cut by a transversal, which is what line R is, then we know that the lines are parallel. That's actually the converse of the corresponding angles postulate. So that means that we have proved both directions of this original biconditional statement that we started with. Two non-vertical lines are parallel if and only if they have the same slope. So now we're going to look over at the next page on page 380. Maria challenged Eric to another proof about slope. She asked him to help her prove that two non-vertical lines are perpendicular if and only if the product of their slopes is -1. So is this a biconditional statement? Well, since it's in the form if and only if, that means that that's a biconditional statement. So the two forms of that biconditional statement that we would need to prove would be if two lines are perpendicular, then their slopes have a product of -1. Similarly, we could say if two lines have slopes whose products are -1, then they are perpendicular. So that's what we're going to set out to prove now. All right, so we've got two diagrams here to help us out. We're going to try to prove that perpendicular lines have slopes whose product is -1. So here in diagram A, we've got lines N, which is increasing, and L, which is decreasing. They're perpendicular. They intersect at point P. Let's highlight point P here. We've also got point S over here that lies on line N. And triangle PRS is a right triangle. That's this triangle down here in the bottom right. Okay? So assuming that A and B are both positive, is the slope of N positive or negative? Well, since this line is increasing, that would give us a positive slope. We want to read the line like we read a book from left to right. So going from left to right, this is going up. The slope would be A over B because this value A represents the rise, and this value B represents the run. So part C is saying, describe how you can use the coordinates of the vertices of triangle P, R prime, S prime in diagram B to find the slope of line L. So now line L is going this way. Okay, so let's see what this says about that. So that would be y2 minus y1 divided by x2 minus x1. So that would be b over a. But the reason that would come out to be negative is because line L is now decreasing. Therefore, the slope is going to have to be negative. Okay, so when we compute the product of the slope of line L and the slope of line N, we get -1. Now let's see how we get that -1. Remember the slope of line N was A divided by B. The slope of line L was in the numerator negative b divided by a. Well, a over a, those a's cancel out. B over b, those b's cancel out. The only thing that's left is the negative sign. And when we cancel out through division, we're left with a 1. All right, so we're going to answer some check your understanding problems about how Maria did her proof. Number 8, describe how Maria transformed triangle PRS to obtain triangle PR prime S prime. Well, it looks like she did some kind of rotation, and since point P is the same in both of these triangles, that's the center of the rotation. And since she rotated it at a right angle and did it to the left, this is the opposite of the way that the clock would go, so that's 90 degrees counterclockwise. Why didn't Maria draw either line L or line N as a horizontal line? Well, that's because the slope of a horizontal line is 0, and that would not help us out. We wouldn't be able to work out that product of the two slopes because another helpful thing to remember here is that when you have a vertical line, then the slope is undefined. So you can't do undefined times 0. That's the one case where the slopes do not have a product of -1. All right, how did we know that the slope of line L was negative? Well, we knew that because the line was decreasing. Going from left to right, the y values are going down. All right, one last problem before we wrap up this lesson. If two non-vertical lines are perpendicular, what can you assume about the signs of the slopes of the lines? Well, to answer this one, we can look at the picture. Here, line N is increasing. Increasing lines have a positive slope. Here, line L is decreasing. Decreasing lines have a negative slope. We can see that when we multiplied our two slopes together, one positive, one negative. So that's a clue. Whenever your lines are non-vertical, if they're perpendicular lines, you know that one is going to have a positive slope and one is going to have a negative slope. All right, so that's it for this activity. Thank you guys so much for watching and for your hard work.